So papers. So the handout we did was basically 12.2, 12.3. And we're going to back up and do 12.1 since the idea of inverse function came up. It makes sense now to go back and say, what the hell is an inverse function in general? So 12.1. Inverse and something called composite functions. So inverse is exactly what you most likely feel it is. So it's the opposite of a function. So what's the inverse function of addition? That's crazy. What's the inverse function of the seventh root of something? The seventh power of something, right? And in fact, each of those things, if I said x plus 4, and then I subtracted 4, I get back to x. If I said the seventh root of x, and then I did a seventh power, I get back to x. It undoes, one undoes what the other one did. And that the word inverse means that. So how do I find the inverse for a function that's a little more complicated? In fact, not that complicated, but the minute I start having a function with several steps in it, it gets more complicated. So So let's talk about first off how to find an inverse graphically. How to find an inverse graphically. So what an inverse function is supposed to do is whatever the original function did, it's supposed to take it back to where it was. So for example, if we had the function, let's say 3 to the x, right? What does that look like? Well, let's get a few values here. What is 3 to the 0? 1. All right, so let me make a little xy table for this. xy, 0 is 1. What about negative 1? What's 3 to negative 1? 1/3. I like it, so I'll put a little approximate right there, 1/3. And what about 3 to the first power? Amazingly enough, that's 3. That's crazy. All right, so those are like my 3 anchor points for any exponential. Negative 1, 0, and 1. Right, unless it's been like really moved around a lot. That's where I try to start. So of course we know it's going to look like asymptotic back there and then crazy over there. Okay. So what would the opposite function look like? What would the inverse function look like? Well, since this one took 0 and made it become 1, whatever the inverse function, and it's really a little unfortunate, but here's a symbol for inverse function. You read this as f inverse. Be careful, it doesn't mean 1 over f, right? You guys with me? The inverse function of x plus 7 should be x minus 7. You guys with me? It wouldn't be 1 over x plus 7. That doesn't make any damn sense. So that doesn't mean it's an unfortunate choice. But, oh well, this is the symbol we use for inverse. It's a function that does the opposite. So what should this guy's table look like? Well, since this guy took 0 and made it become 1, this guy should take 1, make it become 0 again. You guys with me? So so if I had the function x plus 7, what does that do with an input of 1? It makes it become 8. Now the opposite function is x minus 7. Does that make sense? The opposite function of addition should be subtraction. If I put an 8 into x minus 7, I go back to 1. Please let that make sense. Yes?
So would the inverse of 3x be the x root of 3?
Not really. The inverse of 3 to the x will actually be log base 3 of x. Right? Yeah. So this should be 1, 0. And this one made negative 1 become 1/3, so this one's going to take 1/3 and take it back to. So you start to see what happens with an inverse. The x and y just switch. So one guy's output is the other guy's input, and vice versa. Yeah, I like it, because he made 0 become 1, and this guy goes, don't worry, man, I'll take 1 and make it back to 0. I'll get you back there. So 1/3 will become negative 1, and then, of course, it's going to take 3 back to 1. So let's graph that. That's easy enough. Just take the beep. It's almost too nice to believe, but understand why it's that nice. It just takes the output of the first and brings it back to what it used to be. It undoes what was done. That's why it's that easy. But now what's it look like? Well, let's see. 1, 0. Here's 1, 0. 1/3 negative 1. Is that cool? 1/3 negative 1. And then 3, 1. So this is kind of nifty. Can somebody tell me? So see how this asymptote even is going to now be here. I could just draw better. It'd be awesome. Let me ask you guys this question. Where's the mirror for this problem? Yeah, y equals x here. That makes sense, because we took y and x and flipped them. They actually end up flipping over the y equals x line. If you start with a function, find its inverse. We still have to talk about when it's possible to find its inverse. If you find its inverse, it will always be a reflection. That's kind of nice, right? Humans were sort of drawn to symmetry. So it's nice that that's a nice symmetric. And here's the y equals x line. It's going to be the mirror always. So this is what a logarithm looks like. Because we know the inverse of 3 to the x. From that handout, we know it's log base 3 of x. All right, what's log base 3 of 3? 1. Have we all forgotten over the break? Shit. Log base 3 of 1 is 0, because 3 needs the 0 power to become 1. Right? So we could just start here and make a table out of it, but I just started here and did the opposite. And of course it's going to be the table for log base 3, because it is the opposite function. Maybe. So that is what any logarithm looks like. It's going to look like this. Maybe it's been shifted around, but it's going to have that shape. Okay, like it, maybe. So, I mean, any function will work this way. So, if I give you something that I don't even tell you what the function is, which I like to do a lot, if you haven't noticed. So, everybody got what they want from here? So, if I give you this graph here, try to reproduce this. And then I'll get into specifics about how to tell something is invertible. So if I do this, let's see. So this function here, is that a function? Yes, why? Passes vertical line test. I like it. Now let's draw the inverse. So how do I do that? Well, a really smart way to do this, and there's problems just like this in the book. There's going to be problems just like this in quizzes and tests. You don't know what the hell the function is. I'm going to call it g of x. Why not? So I want to graph g inverse. Well, all you do is recover the table. Right? What point is this? Negative 2, negative 3. So what point will my inverse function go through? Negative 3, negative 2. What point is this guy? Negative 1, 0. So my inverse will go through 0, negative 1. 2, 1. So my inverse will go through 1, 2, 3, 3. This is a hard one. My inverse will go through 3, 3. It does not change the sign of anything. It takes the output and brings it back to what the input was. That's all it does. It can't change the sign of it. The only thing the inverse function does is the opposite of what the original did. So of course it's going to take the output, bring it back to what the input used to be. It's going to undo what was done. So now I just got to plot those points. Negative 3, negative 2, plop. 0, negative 1, whoosh. 1, 2, and then 3, 3, bam. Whoosh. And then this is where you get some really, really nifty kind of stuff happening, right?
But it's 3 intersecting points.
So what?
So, is that 3 answers or 1?
There's no answers here. The answer to the question is the purple graph. That's the inverse. Graph the inverse of the black line. Well, the answer is the purple line. It's not, the question wasn't really, it could be, but it's a little bit more than we're ready for. What are the solutions to g of x equals g inverse of that? I'm not going to, that's a little bit beyond, but that could be a question somewhere. And you can still see that y equals x mirror happening there. And you get some nifty shit going on. It's not quite a spirograph. If you get into pre-calculus, you actually figure out the equations behind things. You ever heard of the spirograph thing with the gears and you put the pencil in and you do that and it makes these nifty, some of you guys, yes, some of you guys, well, before the days of Nintendo and shit, and now it's, Xbox and all that kind of shit. We had freaking gears and pencils. Oh, look at that. That's how we pass the time. Okay, so that's one way to do this, to find the inverse, is to take all the points and switch them. Now, is my resultant purple line a function? Yes, it is. It passed the vertical line test, right? So before I do the other way, I want to show you, how do I know something's invertible? Well, I can always do this, but when would the result not be a function? It would be something like, what has to happen? What did I not let happen with that black line so that I knew the purple line would be okay? I don't know, it's hard to kind of tease it out, but that black line is always increasing. Do you guys see that? Or I can make it always decreasing. It just can't come on itself. So is a parabola, is that a function? Hell yes. And if I give myself some points, here's 1, -1, 1. What would the inverse look like? It would have to go through the point 0, 0, 1, 1, and 1, -1. Is that a function? No, because the purple line doesn't pass the vertical line test. So let me do this. Why would I waste time and actually draw the results before I even know it's a valid function? Why don't I just make a freaking horizontal line test, right? If I flip it and then check it with a vertical, let me not even draw the damn thing and check the original with a horizontal. Do you guys see how that matches up? Don't flip the graph and then look at it. Take the graph you got and just look at it this way. So a vertical line test tells you if it's a function. Vertical line test, function, question mark. Horizontal line test, right? The Holt answers the question, is it invertible? I like it. And if it is invertible, we call it, a nifty little phrase, we call it 1-to-1. 1-to-1. Or, sometimes just 1-to-1 like that. Why does that make so much freaking sense? For this black line that I drew, if I tell you an output, can you figure out exactly what the input was? Of course. In fact, we have a list of them, don't we? Here, if I tell you the output was 1, can you tell me exactly the input I'm thinking about? What could it be? If I tell you the output was 1, the input could have been 1 or? So it's not 1-to-1. Every output and input don't go together specifically. It's not 1-to-1. Because that's why this phrase makes so much sense. This is 1-to-1. That input goes without output. Nobody else goes with either one of those things. Bam! That's why you call it 1-to-1. That's what makes it a function both ways. If I have it originally, or if I flip it over the y equals x, it's still a function. So we call it 1-to-1. How are we doing so far? How are we doing so far? I know terminology is always kind of shitty, but oh well.
Is the 3-to-3 still a 1-to-1?
Okay, there's no question about a point being 1-to-1. I want you to realize, see how I go through the mirror? Right? And you can get into all kind of nifty Alice in Wonderland kind of shit, but that's fine. There's no problem to go through the mirror. To be symmetric, it doesn't have to be fully on one side and then fold on the other. No, it's symmetric. If I fold this, it kind of meets, right? So that it doesn't, that 3, 3 is not a problem. The only problem would be is if one point is across from another point, then that's a problem. That's when there's a problem. Then I can't work backwards. And isn't an inverse function all about working backwards? If I have an output that has more than one input that could have led there, I can't work backwards. That's the point. So I could have done a graph that went like this. As long as it's always increasing or always decreasing, that means it's not going to come on itself, right? Okay. So that's how you do it graphically. That's how you do it graphically, to find the inverse. How do I find the inverse? Algebraically. If they give me a function like f of x equals something, how do I find the inverse algebraically? Oh, shit. All right. This is algebra class biology. So we have to eventually do that. The beautiful thing is, how did I do it graphically? How did I do it graphically? I took the xy and I switched them. So how do I do it algebraically? I do the same thing. It's just too nice to believe. So I'll show you what I mean. And then I'll explain why it makes so much freaking sense. Hopefully. So finding inverses algebraically. All right, Jeff. Either spell well or write well. Don't do neither of those. So what if I had f of x? Start off not too bad. X cubed minus 7. Now think about it. Why is this invertible? Do you guys remember what would this look like graphically? Yeah, it would look like this, right? Kind of comes down, and it looks like it's going to be a parabola, but then it doesn't. So it doesn't come back on itself. So it passes both the vertical, as a function, and it passes the horizontal, which means it's invertible. So I'm allowed, if I put a squared here, I'm not allowed to ask you to find the inverse because it doesn't exist. So, screw you, John. So how do I find it? Well, let's bring back y. That's y. There's y, right? And then what I always do is I draw a little dotted line. The reason I draw a dotted line here is because it's telling me that I didn't do anything algebraic to get from here to here. I did a concept. How do I find the inverse function? I switch x and y. Okay, let's do this, and then I'll go back and explain why it should make a lot of sense. In fact, what do you know is going to show up in the inverse? You know there's going to be there's a minus 7 here, so there's going to be a plus 7 in the inverse. There's a cube here, so there's going to be a cube, and I just don't know what order those are going to be done and all that kind of stuff. So if I switch the x and y and then solve for y, I'm going to end up undoing all the operations in the opposite order. So the answer is going to be like the total inverse. Does all the opposite shit in the opposite order. That is the inverse. I used to call it like this little memory thing. It remembers what I had to do to solve. So if I add 7 to both sides, there's the plus 7 we knew. And then I take a cube root. So y equals the cube root of x plus 7. That is the inverse. G inverse, I call it G, right? No, F. F inverse of x is the cube root of x plus 7. All right, let's test it out. Let's test it out. Let's test it out on some specific points, and then we'll test it out on every point that these go through. So that should take a little while. So up here, what is f of 2? What's f of 2?
1.
1. So what should f inverse of 1 be?
2.
It should be 2, and let's try it. When you put a 1 in here, you get 1 plus 7 is 8, cube root of 8 is 2. There you go. Why does that make me feel better? Because it does what an opposite function should do. It should take the 1 and take it back to where it came from. It should undo what this guy did. Now let's formalize what I just said. If I put the inverse function inside the function, or the other way around, what should these two do to each other? Whoa, there's a lot of oohs in a row. What should these Yeah, they should cancel. Just like a cube root and a cube cancel, so forth. These should cancel. It should end up with x. Well, let's try it. Let's take this and plug it into this. And this is where some students are like, what? Sure, do it, whatever. All right, so I'll try. So let me see. What's f of f inverse? Is that the way I said it? Yeah, sure. So I want f of cube root of x plus 7. That's what f inverse is, right? So I want to put this into there. So this equals that thing cubed minus 7. But what happens here? Yeah, these go away. I get x plus 7 minus 7, which is x. So do these undo each other? Yeah, whatever f inverse does to x, f undoes it. Brings it back to x. That's the check. If they say test to see if these two are inverses, this is what you do. Or, you could put f into f inverse and the same thing's going to happen. How do you guys feel so far? Some of you guys look like you should bring some Tylenol with you. Oh.
What did you get the negative 7?
It's in the function. Here, that's what f of x is. So what's f of this? You plug this there. Bam. So minus 7 is in the function that I'm dealing with. Yeah, good. Feel like it. So here, let me see if you guys can handle this. Find the inverse function for h of x equals the fifth root of x minus 2 plus 3. Please notice that that plus 3 is outside of there. I've never seen somebody do that down the line, but to me, I'm like, when I'm doing this, every step I take should be algebraically sound. So the step I take from here to here is not algebra. It's the idea of inverse. So I don't know. I'll stop talking about it, but that's why I put that in. So this one, what do I write? Yeah. So in the process of solving for y, I do end up doing all the opposite stuff. So on that level, this should make sense. So what's the first thing I do here? Yeah, subtract 3. And then, of course, raise everything to the fifth power. Dear God, please don't actually do this. You know what I mean? Don't write it 5 times. And there's no point to that. Please don't. Does everybody understand what I'm saying? Please don't. I don't want to look at that. And I don't want you to sit there and waste time doing it. And then add 2. I like it. So it'll be x minus 3 to the 5th plus 2 equals y, which is really h inverse. Now let's look at this. What's the last operation that the inverse function does? For add 2. What's the first thing this guy does? No. When you plug a number into this, what's the first thing you're going to do? So plug a 7 in. What's the first thing you do? You subtract 2. So the first thing this does is subtract 2. And what's the last thing this does? add to. So that's what I meant. It is all the opposite operations in the opposite order. And if you do this process, you'll always have those two things be true. That's what makes this the opposite of the inverse function. The last thing this guy does is add 3, right? And the first thing this guy does is subtract 3. There. All right, let's look at a funky inverse. Funky. So I'm telling you, going in, this inverse is going to be a little funky. What was that? Okay, let's go back to F. When you do it, you should be like, oh, that's not that funky. So y equals 1 over x. We're just going to do this together because it's a little tiny one. And then what do I do? X equals 1 over y. Now, how do you solve that for y? Huh? I like it. The thing you want to solve for is on the bottom. Well, that sucks. Let me multiply by it. So you get yx equals 1. Is everybody with me so far? And then how do you solve for y? Divide by x. Y equals 1 over x. So f inverse is 1 over x. And it should make sense. If the function is the flipping function, which is what that is, well, what's the opposite of flipping? Flip it again. So the flipping function is its own inverse. It should make sense. Right? If I turn 180 degrees, how do I undo that? I'm going to turn 180 degrees. Holy shit, I'm looking the same way. Is that, you guess, yes? So yes, I don't know if anybody's even possibly considering this, but yes, a function can be its own inverse. There's one example.
So graphically, they just lie on top of each other?
Well, the nice thing, so what does this thing look like graphically? It looks something like this, but Gandalf is now 0. Where's this thing undefined at? 0. That's where its asymptote is going to be. So just to do a real quick, this is what it looks like. What do you notice? How does it already relate to the mirror? It's already symmetric. So when I flip it, doesn't it just fall back on top of itself? Do you guys see what I'm saying? If I flip this around the mirror, doesn't it just fall back onto itself? So it didn't actually change. It's its own self again. So anything, any function that's already symmetric to this line will be its own inverse. So the simplest function that's its own inverse is the y equals x function, the one that actually freaking just lies on the mirror. Y equals x, x equals y, y equals x. So it's its own inverse. Maybe? Okay. I don't know. Part of me is always worried I'm going to have like 5 people take the final, but you guys stick with me. Okay. Blah, blah, blah. So that's, so we talk about a graphical way to find the inverse. Here's the algebraic way to find the inverse. I do want to do one example that's freaky for a different reason. Should this have an inverse? Don't overthink it. What's it look like? What's the graph look like? Just very quick graph, nothing, just a sketch. What's it look like? I asked you to do that. Yeah, there you go. No, come on. What's this look like?
It's just a little
Shot. Right? So how do I know it should have an inverse? Because it passes the horizontal line. It's always increasing, even though it's increasing less and less over here. It's still increasing. The horizontal line is never going to go through it more than once. It is going to have an inverse. So what's freaky about it then? Well, the inverse of it should be, but it can't be true. This can't be true. This can't be true. But notice this. When you flip this thing around, help me out. Let's do some points here now. Let's go against what I just said. There's 1, 1. There's 4, 2. Let's move that up a little. Screw it. Let's make it big. There's 4, 2. So the inverse should go through, and there's 0, 0. So it should go through 0, 0, 1, 1, 2, 4. Is that cool? So notice it's not a full parabola, is it? That's what the inverse would look like. In fact, if I had done them on the same thing, you can see that it still has that symmetry to it, doesn't it? So it's not the full parabola. So the inverse of a square root function is x squared, except what do you have to say? X has to be greater than or equal to 0. Right? So if you go on to something, if you go, let me just push it a little bit, and you guys are like, dude. But oh well. If you get into pre-calculus, if you get into trigonometry, it doesn't really, you don't have to know what the shit this is, but here's a function you'll study in trigonometry. Is that invertible? You don't even know what the shit that is, but is it invertible? No. But what if I do this? What if I only focus on that piece? Is that invertible? Yeah. Yes. So I could restrict my domain, and then it can pass the horizontal line test. So sometimes you have to do that. This should have an inverse. It's not fair if it doesn't, because it does what it's supposed to do. Its inverse, though, is like, oh, if we didn't do this, its inverse is not really an invertible function. That doesn't make any sense. So we just have to restrict its domain so it will match up. Okay. So if I said, so let's see what this really means. If I said, what do you square to make 16, but the number has to be positive, that can only be 4. That's really what this is saying. That goes back to the one-to-one idea. Okay, maybe.
So it's like excluding all the domains that would make it fail the horizontal.
Exactly. It's cutting off that come back on itself part. I like it. Okay. Oh, I was like, what other kind of weird stuff do they do here? I think we've gone through everything they want from 12.1. I like it. Let me just really quick scan, make sure I did everything in 12.2. Yep. Blah, blah, blah. And then 12.3, we got some stuff to finish up. Okay. Oh, okay. So just a few more things. I mean, it's only 1:20, so I got another like 20 minutes before I let you out at our unwritten, unofficial exit time. So coming back real quick to 12.3. So 12.1 is all about inverses. Oh, there's one little thing. Let me come back to 12.1 first. So 12.1 is all about inverses and this thing called composite functions. So nobody really yelled. I think I showed you this before, but just to show you because it's really in your face in this section 12.1. If I said f of x is 3x squared plus 2, and I say g of x is 2x minus 1, let me ask you some warm-up questions here. What is f of 1? Yeah, 5, right? 3 times 1 squared plus 2, yeah, 5. What is g of w? Yeah, just replace x with w, like it's a 2w minus 1. What is g of 5 minus 3x? Don't say anything, just work it out. What is g of 5 minus 3x? Don't say anything out loud. Just work it out. The funny thing is, I don't care what I put in here. I don't care what I put in here. The idea never changes. It can't. Whatever I put in there, put in there. I love that. Come on. Does it mean the next step after you put it in is going to be easy? No, but the first step is always the same. Don't go, oh, because he did this, and that's going to change. No, screw that. So the first step is going to be 2 times minus 1, right? That's the look, and this came up earlier, but the most common mistake is to freaking that poor little dude because you feel like you've written enough. But what's the form of g? Twice something minus 1. Twice something minus 1. And what's the something specifically now? 5 minus 3x. And then you can simplify. So you get 10 minus 6x minus 1, so you get 9 minus 6x. I like it. All right. If you can do this, you can do that. And I think I've talked about this with you already. Because it's just a natural next step. So when we first started talking about functions and all that kind of stuff, I went ahead and did that. This is where they finally catch up to us. But yes, sir.
And what's the inverse for 9 minus 6x? There's no inverse.
That would be another problem. I'd have to ask you another. So nothing I've written up here would need you to do that. Do you see what I'm saying?
Okay.
But if you want to investigate that, we could do that as another problem. So it's not really a part of this.
All right.
But we could do that, sure. So how do I do this problem? Well, this is g of what? 3x squared plus 2, yeah. So we replace the inside with what it is, and how does that match up with how we do anything PEMDAS and all that kind of shit? We start from the inside. So what is it in the inside? That. Okay, now I put that. It's inside what? It's inside this function, so I just put it there again. So this becomes twice. Yeah, twice something. I like it. Minus 1. And what's the something now? And then you can get 6x squared minus 1 minus 1 minus 5. I like simplification should be quick. Right? This is what they call composite functions, because it's a function composed of another function. And the unfortunate symbol that is used, this symbol is already here, and it makes the most freaking sense in the world. Plug f into g. I mean, you can just see it. Unfortunately, your problems in the book will most likely start with this bullshit. I'm sorry, I shouldn't say that. Excuse me. Fellow math people, don't excommunicate me. But I have to be honest, I mean, there are a few places where this kind of helps, but it doesn't really help that much. This is the good old goof function, right? This means g of f of x which is already what this says, right? Or g composed of m, it just takes it away from the idea. So if they ask you, what is this? The very first thing you write for yourself is that. And then you can work it out. You just translate what they're trying to ask you. So how would you do this? I like this one because students tell me that's how I feel. I'm in a fog. Well, let's rewrite it first. Let's see. Well, how would I rewrite this into a better form? This would be f of g of x. And then I can replace what? G of x is 2x minus 1. And then I want to put 2x minus 1 into f. And what's this going to entail? So this would be 3 times something squared plus 2. And the something now, of course, is... And then this you have to square, you FOIL it out, multiply with it. I'm not going to do it. You guys can do that. But once you plug it in, then you just simplify whatever the hell there is to do, which should be relatively simple.
Do we ever have a 12.1 is like inverse functions of g of x and stuff like that?
Could be, yeah. Oh, yeah.
What we learned in the inverse, what you just showed us how to do the inverse, and plug it into the g of x.
There are some problems where they give you, well, you just got to get in there and try them out and then ask me. Yeah. Okay. Let's try it. Let's see what you think about this. Sorry, G. What about g of 1? That's the g. Yeah, again, Russian nested dolls, but somehow we magically start with the inner one, right? So I got to know what g of 1 is before I can put it into g. And then I got to know what the hell that is before I can put it into g. Don't freak out that there's g's in a row. Who cares? G is a function. It could be plugged into any other function, including itself. So this is well, what is g of 1?
1.
Yeah. And what's g of 1? 1. And then what's g of 1? 1. Now that's please, dear God, realize that that's just a coincidence. Don't always go f of is 7. 7, yeah, because that's what he did. It just happened to be, if I would have put a 3 here, that would have been completely different, right? So here, so what is f of, what's the matter, Jeff? Negative. That last step will be a nice one. That last step is a doozy. 5929?
It's 1520.
5929. All right, well, let's find out. Let's do it. 5929 times 3, I can't do any more than that, but I don't know. Somewhere you're going to have to know what 77 squared is, I think, if I did this right in my head. So what's f of negative 1? Start there. 5, is it cool? Negative 1 squared is 1, times 3 is 3, plus 2 is 5. How do I do f of 5? That'll be 5 squared. 25 times 3, plus 2, 77. So what's f of 77? It'll be 3 times 77 squared plus 2. Now I forgot what I said. Oh, shit.
5920.
5929, I think. And that's what it is? Hey! Real quick. I don't know if I ever showed you this, but to do 77 times 77, I know everybody's like, I got this thing. It's called a calculator. Jeff. This is how you do it in your head. You make a little FOIL problem. 4,900 plus 490 plus 490, so plus 980 plus 49. And then in your head, it's quick. Anyway, so that, I forgot again what the hell. If I only had a memory, I could do a lot of shit. 5929. 5929? And whatever the hell that is. I mean, it's, you know, plugging together, who cares? The important thing is you're able to interpret what this is asking you. This is the negative 1. So you just keep plugging it back into itself. Get over that. It's a function. You can plug it into any function. Okay. So, let me see. The last thing for today, which is actually going to be sort of a big thing. So I'm just going to get us a little bit into it next time I have a handout. Is properties of logs. Let me just say logs. Bam. Properties of logs. This one gets, well, let's see how we go with this. I'm going to show you the first property. I'm going to show you a proof of it. The proof is well, we'll see. Let me just not even tell you anything. So here's the property 1, the first property of logarithms. Log base anything, log base A of m times n is log base A of m plus log base A of n. Now that is freaky. You've never seen anything. Now notice this does not say multiplication equals addition. This does not say something like 2 times 3 equals 2 plus 3. This doesn't say log times log equals log plus log. It doesn't say that. In fact, really look at it as a different way. Logs are powers. So when I have two things with the same base multiplying, what do I do with the powers? I freaking add them, right? So that's what I meant by all the properties of logs are the same as the properties of powers, because logs are powers, right? Now, be careful. The other way around doesn't work worth shit. If the inside is plus, it doesn't equal log AM times log base N. A-N. That's bullshit, right? It doesn't work that way. I'm trying to show you a proof, and then I think I'll let us out here a little early. Why not? All right, it's fine with me. I was out a little late last night. Where'd you learn? So let's do this. Let me say log base A of M. So this proof requires, this is how proofs sometimes work. We already should be familiar with, somebody tell me, what is log base A of M? Just tell me, what is log base A of M? I love this question. What's log base A of M? I don't frickin' know, right? That's a valid answer. I don't frickin' know. So in algebra, what do we call something when we don't know it? I love it. And this helps me just work with it. So this is a proof technique. And why is it okay to do this? Because I can call any damn thing I don't know X and then work with it. It's just a placeholder in that respect. So what do you think I'm going to call log base A of N? That's insane. All right. I wanted somebody to say like W. All right. Okay. So now watch. How do I say this? So what does this mean? Let's see what this means. Interpret this for me. What does this mean? This means a to the x equals m. And this means a to the y equals n. I like it. I like it. So then what is m times n? Yeah, m times n is a to the x times a to the y. Which is?
A to the x, right?
A to the x plus y. Right, yeah, we know so far. I mean, nothing I've done yet is really that crazy. You got to get over this. I can just call anything x, really. I just have to bring it back eventually, what it really is, but I can just placeholder with x. Now, this calling it x allows me to write this, which allows me to do more than if I didn't do that. This is all valid, though. This does equal something for certain inputs. Okay. So what is... So this leads to this, which then, why did I do m times n? Because I'm trying to investigate this expression, right? So I want to know, what the hell is m times n? So what's log base a of m times n? Well, it's log base a of... What is m times n? A to the x plus y. And now we should be able to do this a little bit easier, right? What is log base a of a to the x plus y? X plus y, right? Another good way to look at it is these cancel because they are inverses. But what was x? X is log base a of m. And what was that? Oh, what was y? And so I've proven that that equals that. I feel like this is, I don't know if you pay anything for that show. But I mean, it should have hopefully made some sense from the beginning before I did any of this. In fact, I'm always worried that this made it worse for somebody, but this is the true proof. But what I said earlier hopefully should make sense. The power on the result of a product of things with like bases should be the sum of the powers on each. I mean, that's like a definition of the power, how powers work. So what do you think? I know I'm lying now because I said I was going to do one, but I don't care. You already know that about me. What do you think is true then about log base a of m divided by n?
Subtract
Holy shit. So it'd be log base a of m minus log base a of m. Yeah. Because what do you do when you divide things that have like bases? Because don't they both have a base of a? Yes. You subtract the powers on those things. Beautiful. This is what I mean. Now there's a couple more, but I think I'm not going to push it. I want to wait till I get that handout to you guys. I will do this one. Just to show you a concrete example. I mean, if I'm you, I want some freaking concrete examples. I'll show you one concrete example, and then if I don't let you out after this concrete example, you can kick me. All right? Everybody's like, I kind of want him not to, so I can just kick the shit out of this dude. So what if I had log base 7 of 98 minus log base 7 of 2? Do you know what either of these things are? No. And we don't really have a great way to figure out what they are either. But what property can I use? Yeah, they both have the same base. So subtracting powers must mean I was doing what with these things? I was dividing them, because I'm subtracting powers. That means I was dividing. And 98 divided by 2 is 49. So log base 7 of 49 is 2, because 7 squared is 49. So that's an immediate, concrete example of how we can use these properties. All right. Since I don't want to be kicked out.
And if we have multiplication, we just add them together, right?
Say again?
Never
Yeah, this first one?
Yeah.
Okay. I was worried if you were going to ask me something new, somebody might interpret it mean, I can kick them. Yep. I'm going to stop bringing that possibility in. All right, guys. What was I going to say about next week? Forgot. Well, we just started doing new stuff. The soonest we'd have a quiz is Tuesday, but we'll know better Monday. I'll probably have a quiz on Wednesday, to be honest. Okay? All right.
So, Joe.